it is Friday, which is a very nice thing, at least for me. Let's get started. Let's talk about some compilers, then you can get your weekend started. So we are still in Module 2, which means we are still doing syntactic analysis. But it's one of the last lectures on it. We'll do it today and maybe a bit on Monday, and then we're moving on to Module 3, which is intermediate representations. But I think these last few lectures will really tie things together. We've been playing around kind of with specifying grammars. We've been using ply as our parser. But today we're actually going to talk about a parsing technique called recursive descent parsing. And I think it's actually pretty cool because it allows you to write your own parser, similar to what ply is doing for you, right? Ply is taking your grammar, and then it is making a parser for you. You get a turn to actually make your own parser, and what you're going to see is when we have the help of these first and follow sets, you can actually write some pretty simple parsers using this style. So, exciting stuff. Let's get into it. As always, let's start off with some announcements. So homework 2 is due Monday at midnight, so that means you have this weekend. That means there are some office hours remaining in the time. You also have Piazza, but as a reminder on Piazza, there's no guaranteed help over the weekend or off business hours. But yeah, so you still have a bit of time to get some help. You have everything that you need for the entire assignment. In fact, you had it at the end of last lecture. This time we might clarify a few things with like first and follow sets though. So, all of this will help. And just as that reminder that some people are seeing is you don't actually need to return anything from the parser in ply. The only thing ply is helping you with here is so that you can test your grammar, so that you can try feeding in some strings, try testing, you should have an idea of what valid strings are because they're very similar to C, and you can try feeding that into ply and seeing if your grammar accepts it or rejects it. Otherwise, if you do this on paper and pencil, you kind of just have to write it out by hand and do the parse tree. So, ply is here to kind of just help us evaluate our grammars, both so that you can evaluate it and see if it's behaving how you think it should, but also, for us to help give feedback on it as well. So, yeah, you don't have to return anything from your parser. Yeah, I know there was a little bit of friction with the autograder, but everything should be working well now. The TAs put in some simple sanity checks for you. So if you've noticed, it was updated with a couple of tests. Those aren't comprehensive. We will run tests that aren't there, but they should be good to help you get started. And again, you should write your own tests because it's part of working with compilers. And just want to say thanks to people who have worked with us, who posted on Piazza. This is, like I said, a new way how to do this assignment. So there was going to be a bit of friction, but I think it's in a good place now. And so thanks to you guys. Like I said before, compilers is part programming, and it's what you're doing. It's the source code that you're writing. But there is a decent chunk, and when you go and work in compilers in the real world, you're not going to have people feeding you test cases. You're going to have a PDF written by 20 different people that is in much worse shape than the PDF you have here, and you're going to have to iterate back and forth on what this means, what test cases are, and so on and so forth. In my personal experience, I'm a member of the Kronos group. We do GPU programming languages like Vulkan, OpenCL, OpenGL, and every single meeting is essentially like a Piazza post like what we have. We get on the phone call and people show a program and they say, is this program okay? And so, the hard part isn't necessarily writing the parser or the compiler. It's kind of agreeing on what the language should be and what it should mean. So this is all kind of part of the study of compilers, which might be a little bit different from what you're used to if you're kind of used to just, like implementing a stack. We know how a stack should behave. Part of it is figuring out the language. Yeah, Josh? Yeah, so that's how compiler research goes, right? And you can look at people who are designing new languages, and they'll say, what does this test case do? They'll talk about test cases and stuff like that. The compiler is mostly written in. So, but it's like, you need to think about what's valid, what's invalid, what sort of syntax errors should be thrown and stuff like that. And so a lot of the conversation and evolution of compilers is in the form of coming up with your own test cases and thinking hard about, in the documentation where something isn't quite so clear. This is why, Python and C++ continually evolve their documentation, because you find places that aren't so clear or you add features. But yeah, it is just looking at a lot of test cases. And that's why in a lot of modern compiler research, it is automatically coming up with test cases. People come up with interesting ways how to test compilers rather than coming up with compilers themselves. So yeah, yep.
We already got points on grade scope. Should we rerun the grade scope, or is it already automatically coded?
It should be rerun for you. You can submit it again and see if you pass all the tests. If you're confident in your implementation, you should pass them. So yeah, just some extra sanity checks for you to double check. All right, any other questions? Okay, and like I said, it's fine to discuss individual test cases on Piazza or with classmates. If you have a test and you say, I don't know if this works in the compiler or not, I think it's fine to post it. And sometimes the answer is pointing back to the PDF. Sometimes the answer is scratching the head a little bit. But this is all part of the process. So that's totally fine. What I would say is just don't share big repos of test cases with scripts that automatically run them, because I think part of the value is in thinking about the test cases and thinking about what happens with them. Okay. We went over this last time, but midterm study guide, I'm kind of just reproducing these slides in case you want to come find them again. I want to make them easy to find. What we're going to do is either today or next time we're going to talk about symbol tables, so we'll make sure to cover those in class. We're also going to talk about recursive descent parsers. And then, once we cover a couple of classes on Module 3, like I said, the study guide will essentially just be a couple bullet points on what we talked about, but there shouldn't be any surprises. Okay, so that being said, I know we talked about it a little bit, but how's it going with the homework? Do people have any questions right now? Or people have any experiences? Yep.
For the ignore token, are we supposed to use a special built-in variable that the library uses?
I believe it's if you do t_ignore in lowercase, that's a special symbol, and it will ignore whatever characters are in that string, but it's not a regular expression. So you can do t_ignore equals space, new line, tab. It'll ignore space, new lines, and tabs. The other thing you can do with ignore is you can make your own token, maybe call it capital case ignore, make a token action that doesn't return anything, and that's how you can count line numbers. That's what it does in the documentation. So there are a few ways how to do ignore. And it describes those in the docs. And?
No, nothing.
Okay. Yeah, anyone else? I thought I saw another hand. Yep.
Are we being graded on part 3?
So we have a grader behind the scenes that we'll use. So not providing all the graders that we use. So yeah.
It just checks it against parser.out.
Yeah, we parse in your parser.out, and then we generate the first and follow sets and then compare it to what you have. You do not have to algorithmically generate your first and follow sets. You can do it by hand. The book, if you've looked at the book does give an algorithm for it, and that's how we do it. But you can just do it by hand. Yep.
How do you do the line number in for Yak? How would you do that?
So the line number, there's an example in the documentation. What it is you make a new token for new line. You give it a token action. So that means you implement it as a function. The regular expression is going to be the doc string. And then this particular lexer has a line number member, and you can increment that and don't return anything, because if you don't return anything, it will ignore it. So there's an example in the specification. If you just open up the lexer and search for new line, you'll see it, but that's roughly the idea. Yep.
I think there was a Piazza post about this, but there's talks about AST construction. And
Yeah.
I looked into it on the documentation, and at first I did implement it, but I commented it out before I submitted the grade scope, and it was totally fine.
Yeah.
Are we going to do stuff like that next week?
Yeah. Well, probably in the next 2 weeks. The first thing we're going to do is we're going to write our own parser. So we're going to do what basically Ply does for us. We're going to have a chance to actually do it ourselves. We're going to do it in a much simpler way than what Ply does. And we're going to talk about that today. And then from there, we are going to generate the AST. So yes, it's coming. Good question. Emrata?
For the follow sets, if none is an option, should we just type the Python none?
Yeah, type the Python none. Yep. Yep.
Is the next homework released on Monday?
Yes, plan on next homework released on Monday. Yep. If you have all of the ingredients from this homework, the following homework should just lead directly off of that. So basically, this is a way to prep yourself for the next homework. Yep. And we will be releasing a solution. So that's why we can't accept this homework late, because we're going to release a solution in case you totally tripped up on this one. You'll have a solution, and that can guide you in doing the next homework. Yep, good question. Anyone else? Okay. So just to kind of look at it a little bit, I was going to go over just a little bit of Ply, just so, I know everybody's probably started it, but this is just from the calculator example in the documentation. You have your list of tokens. Tokens are just strings in this case. Here we have number, plus, minus, molt, div, left parenthesis, right parenthesis. We define them. So here's that ignore built in. You can have t_ignore. And for example, here I'm saying ignore a space or ignore a tab. This is a bit different because it's not a regular expression. It's just a list of characters to ignore. And then, actually, let's see. That's a different one. So same thing here. Then, what happens is you build the lexer, and then here's just some very simple expression rules. So here we're saying an expression can match a number. You don't have to return anything. In this case, I'm just following the Ply example, which returns that number parsed as an integer. And then, for example, you could have a plus expression, which is an expression plus an expression. So the question is I know this isn't a complete grammar, but what else is wrong here? Some of you have been working on your homework. No. Simon?
The X for plus is ambiguous.
It is ambiguous. And you can tell that when we go to run it. You can see how Ply is warning us is this thing that says warning, one shift reduce conflict. What that means is underneath the hood, when it's building the parser for you, it realizes that there's a choice that it can make. And so it's made that choice for us. Who knows if it's the right choice or wrong choice, but it's warning us and saying that it did. But the nice thing is now in that little calculator language, we can do something like 5 plus 5, and it gives that to us. How would we resolve this ambiguity? Yep.
I was just wondering, is that a good way to tell if your language is ambiguous? Like, it will tell you for sure?
Yes, exactly. And that's a decidable problem, because if you don't see that warning, your grammar is not ambiguous. That means that as it built the parser, there were no places where it had to make a choice.
Okay.
Yep. So that is a deterministic thing. Yep. So how do we get rid of this ambiguity? Can we change our grammar really easily? What do you think? How do we change it? Who wants to say? Yep.
Should we make the left expression num?
The left expression num. Let's try it. And we see that shift reduce conflict warning is gone. So this is no longer ambiguous. Doesn't like that for some reason. But, so the question is, well, it doesn't like that because this is actually a string, so we need to cast that to an int. Does this work? Let's say if we wanted to do a minus. So if this is minus. Now our calculator can hopefully handle minus. 5 minus 5. 5 minus 5 is 10. Forgot to change this. Yeah. Okay, so no longer ambiguous. We could do 5 minus 5. That's 0. Okay, so that's behaving how we'd want. How do we tell? So it's not ambiguous. That's a good start. How do we tell if we got our associativity right? Max? 5 minus 5 minus what?
5.
Minus 5. What would we expect this to be? But it's 5. So, what happened here? If we go into regular Python, we do 5 minus 5 minus 5. It is negative 5. But what we can see is if we wanted to actually get that 5 back, it means that we're actually evaluating it from right to left. So To fix this, actually, when you have left to right associativity, you recurse on the left side. So now, let's try it again. 5 minus 5 minus 5. And of course, I'm going to make this int. 5 minus 5 minus 5. And now we get what we think it would be. So there's probably a little bit of tension from what I just did and what we learned about last time. And what is that tension? Max? Exactly. So, like what Max said, last time we said top-down parsers, they don't like left recursion. But I just said, to get our associativity right, we needed to recurse on the left. So how do we resolve this, if you remember from last time? Do you remember? Namrata?
You would have like another definition for like if you had expression plus num, like you would move it around, but then you would have another definition would be like plus expression 2, and then you had like the original one, you just have like expression 2 and it goes down to it.
Exactly. There's a recipe for it. So let's get to that in a second. We're a little bit out of order. Let's make sure that we have time to talk about the quiz, but we'll get to that. And in fact, this first quiz question has to deal exactly with that. So the first quiz question is, to prepare a grammar for a top-down parser, you must ensure that there is no recursion except in the rightmost element of any production rule. Who says that's true? Who says it's false? How do you fix this? What's wrong with this statement? We just barely talked about left recursion. We can't have left recursion, so what's wrong with this? Yeah?
To say no recursion in the leftmost element.
Yeah, exactly. You can have recursion like in the middle. It's just that very left element that you can't have. And so if remember, the problem with left recursion is in our algorithm right here, when we have a grammar that's nice like this, but it has left recursion, when you pick your next rule, potentially you just pick and keep picking, and you can keep expanding expression into expression into expression into expression. That can give you infinite recursion. So what we do is we eliminate left recursion. And there's a recipe. Every context-free grammar can be written in a way that isn't left recursive. And you do that by applying this recipe. So this comes from the book. You can have phi is equal to phi followed by a or b. You write a new you make a new production rule, phi2, and then you say phi is equal to b followed by phi2, or a followed by phi2, the empty string. And this a and b can really be any sequence of terminals and non-terminals that we want. So for example, if we have our simple little expression language like we have here, we have left recursion with this expression and expression. When we change it to a non-left recursive grammar, what we have to do is we have to figure out what a and b are. Well, in our recipe, phi is followed by a. So a is op unit. Op unit. B is what comes after. So B is just unit. And now that we have that, we can apply our recipe, which basically says our original one goes to B, so unit expert 2, and this one goes to A, which is op unit expert 2, just applying this recipe, and this comes down and is empty. So you can rewrite any production rule to be non-left recursive using this recipe. And you will be needing to do that in your homework, because to get left associativity, you need to first have left recursion, and then you need to adapt it. Now, does that ruin your left associativity? No, it doesn't, because you still recurse down on the left-hand side. What it just means is that you don't directly recurse on your leftmost component. Okay, so how about this one? It's only possible to write a top-down parser if you can determine exactly which production rule to apply at each step. Is that true? Is that false? Some people say false, some people say true. Well, if you remember, what we said is in kind of this big algorithm that we had, what we can do is we can actually cache the state here. When I say cache the state, that means that we have to cache the entire lexer. We have to cache what we're looking at. We basically cache everything in our derivation table up until we make the choice. So if we're trying to match the string A, all of a sudden we're going to get to the point where we have ID expr2, and we have a choice. We can apply this rule, or we can apply the empty string. Well, if we make a bad choice, if we try to apply rule number 2, what we could have is ID plus expr2. Well, we're just trying to match A. We would realize that we can't match plus because there's no plus there to match. And so what we could do then is if we have that state cached, we could backtrack, get rid of that, and make a different choice here for expr2, which would be the empty string, and then we just get ID, and then we could match A. So, of course, it helps if we can know which rule to pick. That helps, and we are going to get there. But strictly speaking, you don't need to know. You just need the ability to, cache the state, and you need the ability to backtrack, which basically means popping up to the last step you cached and making a different choice. Now, that is a huge pain to implement, and we are not going to implement that, but just know that it is possible. Okay, so some of you, are at this point in the homework right now, and this is really what we've been talking about quite a bit. And you actually have hands-on experience with this playing around with ply. This says, in many cases, a top-down parser requires the grammar to be rewritten to avoid left recursion, for example. So, when you're developing a compiler, do you want your grammar to be written in a non-left recursive way, or do you want to, use a different algorithm? When you think about a grammar, is it easier for you to read something like this, or is it easier to read something like this? Who thinks which one's easier? What do you think, Max?
The left recursive one makes a lot more sense than that.
Yeah. I kind of like this one. What do people think? Why does this one make sense? Yep.
I mean, like each operation or expression recursion has one production, and you can look at all of that with that. But then the other one, abstract it not to read left recursive, but also for reading it, you have to think about what that abstraction actually does.
Yeah. When I think about it, it's like, what is an expression? An expression is one expression with an operator and, a unit or a term or something like that. To me, that just reads kind of like how I would describe an expression in English. And like, for example, what the specification in your homework, you can kind of read the English. And I know, there might be a few things that you don't need to scratch your head on, but those English descriptions really map to these production rules. But when you have to, get rid of your left recursion, it's really hard for me to even kind of say in English what this is. An expression is a unit followed by an expression 2. An expression 2 is an op unit expression 2 or empty. I find that, these non-left recursive production rules are not as nice. But the benefit is if you rewrite your grammar, you can use a top-down parsing algorithm. You can use essentially this parsing algorithm, and in fact, a much simpler one that's coming up. So you sort of get this trade-off in that you spend time massaging your grammar into something that's easy to parse, or do you, need to write a crazy parser to handle left recursion? Because what's happening in ply, because ply is a parser generator, it's made the decision. It says, I have all this stuff automated. You can write your grammar however you want, and I will deal with it. But that's because it has the complicated parser that's in its backend. Yep.
Could you kind of clarify the difference between direct left recursion and then just like left recursion?
Yeah, so I mean they're really the same, very similar. So when we have direct left recursion, that means you have a non-terminal like expression, and then in its options somewhere, it refers to itself. So it's sort of a self-referential recursion. Indirect left recursion would be if you have to move to a different non-terminal to see, and so you kind of have to take a round trip. So for example, I know this is a little bit bizarre, but if this referred to an expr, that means that there's left recursion here, but to get there you have to go to a unit, and from a unit you have to go to expr, and that comes back up to expr. It means you have to take a round trip through another non-terminal. That's indirect left recursion. They're both left recursion. In both cases, your top-down parser will not like it. In most cases, the left recursion you see will be direct left recursion. Just in programming languages, you don't oftentimes have this indirect left recursion. But that's indirect left recursion. Yep.
Do you have time to make a more concrete example of like left recursion occurring?
Oh, like indirect left recursion?
Or just direct left recursion? I'm just trying to understand like
The,
what
the,
exactly causes this.
So this is direct left recursion when you have a non-terminal, and in its rules, one of the rules in its leftmost options is itself. So it refers to itself in its leftmost, right? So non-terminal, look at the options. One option's here, one option's here. There's no left recursion here. Look at the other option. There is left recursion here because it refers to itself in its leftmost, the leftmost symbol here.
Yeah, I mean, I was just wondering if you had like you can like come up with an example that will like
That has left recursion?
the algorithm. I'm just trying to like.
You want an example of a grammar or in the algorithm? Because in the parsing algorithm, the reason why you run into trouble in the parsing algorithm is because you have to pick your next rule. And there's always an option here. When you're expanding expression, you can always say, I'm going to expand expression, and I'm going to keep expanding expression. And you end up with something like this, where you just keep expanding expression on the left, you never make progress, and this is infinite recursion. So that's why you can't have left recursion in a top-down parser. Because in a top-down parser, you see a symbol and you try to expand it. And then you find the next symbol and you try to expand it. You find the next symbol and try to expand it. If that symbol that you're expanding is always on the left and is always yourself, you just keep expanding it and it keeps growing and you never make any progress, right? We're never like matching a string. We're never matching a parenthesis because we just keep picking that expression rule, and there's really no way out of that recursion. So that's why top-down parsers cannot handle left recursion.
So C is getting parsed as a unit, but A plus B will keep getting parsed as expression.
Well, the question is
That's what I'm trying to like. That's the question I'm asking. Like, what would it look like when you're trying to use that string and then put it through that algorithm?
yeah, so when you're going through the algorithm, this is the big thing right here, is when you pick the rule to expand. And right here, we are always seeing expression. So when we pick expression, we can pick this rule or we can pick this rule, right? Expression has two choices. Because this is the leftmost thing. We constantly need to make a decision between 1 and 2. And so the problem with left recursion is you never know when to stop picking this rule number 1. Because if you pick rule number 1, the next thing you need to expand is an expression. The next thing you need to expand is an expression. You keep going with expression indefinitely.
So A plus B in the parentheses will keep getting expanded?
No, because we don't even know A plus B. In order to get A plus B, we need to make it to our lexer. Our lexer has this token, left parenthesis. We don't get to left parenthesis till we get to a unit. But there's no chance to get to a unit because we keep recursing indefinitely. We just keep picking this rule number 1. That is an option. That can happen in this algorithm. So before we even get to a token to match, that's the problem there. Where if we rewrite the grammar into something like this, there's no left recursion. Eventually we see a unit. When we see a unit, eventually we have to match that. Or eventually we see an op. If we see an op, then we match plus or multiplication. Or when we see a unit, we match that. We have to make progress. There's no way to just infinitely recurse on a symbol. So spend some time with it. Go read the book chapter. It's there. Recursion is not a simple concept. There's a reason why it's known for being one of the tricky things in computer science. James?
In the book, it mentions oracular choosing, which is like the perfect, like you pick the next perfect rule.
Yeah.
So that will occur even if it picks the perfect rule every time.
No. So if you can pick the perfect rule, you can come up with a left derivation. You can handle left recursion. The trick is this is taking us a step in the direction where we no longer have that miracle, right? And if you don't have that miracle, then you never know when to stop here. And I can always construct a string for you that will stop at different places. Like I can always make longer strings that say you have to recurse 10 times, 20 times, 100 times, and you never know when you have to stop. So it's just a non-starter. Like, you'll just never know when to break out of it. Okay. Yeah, good questions. Okay. So you can't have left recursion in top-down parsers. Let's see. So what we then want to do is make a parser that is backtrack free. And when I say backtrack free, what I mean is I don't want to have to cache the state. Caching stuff is annoying. If you have to cache it, you have to cache the entire lexer, you have to cache everything you're looking at, and you also need to have some mechanism so that you don't pick the same rule twice. I think we can all agree we've probably written backtracking algorithms. They're not fun, they do exist, but if we can avoid it, we don't want to do it. So, a question to kind of motivate this is, if we are just trying to match the string A, and if we make it to this point, we start with expression, we have to expand that to ID expression 2, we have a choice here. And the choice is we can either pick rule 2 or 3. What we can do is we can actually make a smarter choice. We are trying to match A. Well, we can do that with an ID, but then what we have to do is we have to expand expression 2. And now that A is matched, that's all of our strings. So the next thing we have to match is none. It's the lexer is over. So because we know that we have to match none, we don't want to pick rule number 2, because if we pick rule number 2, that's saying we have to match a plus next. We have no more pluses. We have no more characters. So this is telling us, intuitively, we as humans can see that we want to pick rule number 3 there. And the idea is that we want to be able to codify this. We want to be able to come up with rules so that we can know exactly which rule to pick next. And so to do that, this is why we have the first set. Now remember, what the first set is, the intuition here is that we want to know which rule to pick next. And we want to be able to figure out that rule depending on the token that we're trying to match. So let's see. So the thing is if we're down here, if we are matching an op, and that gives us 2 choices. We can pick 6 or 7, because op can be 6 or 7. What we know is, depending on the token that we are currently looking at, if the token we are currently looking at is a multiplication, then that's, we want to pick rule number 7. So the first set essentially says, for each rule, what is the first terminal that you are going to have to see if you make this choice? Or what is the set of the first terminals you are going to have to see if you make this choice? So if you are going to pick rule number 7, the token that you better be matching next is a multiplication, because that's the first thing you're going to see. In fact, in this case, it's the only thing you're allowed to see. So you're going to have a multiplication there. If you pick rule number 6, the first thing that you better see, or that you want to match next, had better be a plus. And in fact, that's the only thing you can match there. Moving up to a unit. If you pick rule number 5, the next thing that you better want to match is an ID. That's a terminal. So that's fine. If you pick rule number 4, the next thing that you need to match is an open parenthesis. Actually, for consistency, I won't do that. Okay. Empty strings, they're a bit special, so they just go in the first set. Okay. If you're going to pick this rule, number 2, that means that the first thing that you need to see, that you need to match, is an op. Well, an op is a non-terminal. But what you do is if you come down here to op, you say, if I pick an op, that means that I am going to need to see one of 2 things, plus or multiplication. And if you have the first set for op, you can just take the union, because you know everything that you're going to need to see if you match on an op. So we see an op here. We can take the union of the options for op, 6 and 7. So that can be a multiplication or a plus. So essentially you're saying, if I match this rule, if I pick this one, the thing I better be trying to match is a multiplication or a plus. And I know that because when I drill down into op has those 2 choices of plus and multiplication. Similarly, up here, if I pick rule number 1, it's a unit. Well, a unit, we have the first set for that, is an open parenthesis or an ID. So if I pick rule number 1, it better be an open parenthesis or ID. So these are the first terminals that we need to see if we pick any of these rules. Okay? And now we can use those rules to determine which rule to pick. So for example, if we are picking the next rule, that means our focus is a non-terminal. Let's say our focus is a op. So if our focus is an op and we're picking the next rule, that means we can pick between 6 and 7. Well, our to match is the next token that we need to match. So we know the token that we need to match. And if we are trying to match a plus, then we better pick rule number 6. If we're trying to match a multiplication, then we better pick rule number 7. So you essentially look at your first set and you look at your to match, which is the next token that you are trying to match, and you use that to guide you on which rule that you need to pick. Now, the empty string, that one gets a little bit, I don't want to say confusing, but empty string is always for free. We don't have it here, but remember, when you see the empty string, that basically, every string kind of starts with the empty string, so you can kind of just pop that one off regardless. What we need to do is when we see the empty string, we need to compute what is called the follow set. So this is similar to the first set. The first set is the terminal that you need to see, the set of terminals that you need to see if you pick that rule. The follow set is the terminal that can come after you are done matching your non-terminal. So for example, technically the follow set is defined for every non-terminal. We just put an NA here because you only really need it when it is the empty string. But you could ask, for example, what follows an op? Well, what we have to do is we have to go up, we find op. Well, a unit follows an op. Well, let's see. What is a unit? Well, a unit, the first terminal that matches on a unit is open parenthesis or ID. So, if you were trying to find the follow set for an op, go find what can follow an op, which is a unit, and that becomes, open parenthesis and ID. So then the question is we need to find the follow set for the empty string. This is essentially what's going to guide us to make this choice. Because right now, using the first set, we never have any information that would allow us to actually pick this, right? Because we're never going to have a token that's the empty string. But it does make sense. We are going to need to pick this rule occasionally. So we need to figure out what can follow an expression 2. Well, we just need to look in our grammar and we need to say what can follow an expression 2. Well, we have expression 2 here. Nothing really follows it there, so that's fine. We also have an expression 2 here. So an expression 2, what can follow it? Well, we're at our top level production rule. So because we're at our top level, we can actually just end here because this can be the end of our string. So none can be the terminal that follows there. Or we can say because we are at the end of expression, what can follow an expression? We need, as long as we're at the end, we kind of recursively need to keep looking. And so we'd say, what can follow an expression? Well, expression is here, and another terminal that can follow is close parenthesis. So now you get that. So you essentially need to go and you need to find what terminals can immediately follow an expression 2. So we have that now. And what you can do is you then can merge those. You take a union of the first sets and the follow sets, and you get what's called the first plus sets. So again, that's in your book, and what we'll be using to make our parser. Now, what you do is you look at each non-terminal. If every production option has a disjoint first plus set, then we do not need any backtracking. So for example, an expression, here's the first plus set. We only have one, so if you only have one, that's fine. No problem here. Expression 2, we have 2 first plus sets. We have plus and multiplication, none and closing parentheses. These 2 are disjoint, which means when you are parsing and when you need to make a choice, you come to an expression 2, you need to pick 2 or 3. You can always make a decision. You can say, I'm going to go for 2 if I have plus or multiplication, or I'm going to go for 3 if I have none or in closed parenthesis. And what if I have something that's neither, that doesn't fit into any of these? then that's a parsing error. That's how you can actually determine. That's how you can actually get the error. If somebody's forgetting to close a parenthesis, if somebody's forgetting to put a semicolon, what you will do is you'll have a token that doesn't match your first plus sets. Okay, when you make it to a union, you're going to need to make a decision. Are you going to expand 4 or 5? Well, that depends on the next thing you need to match. If you have an open parenthesis, you have this one, or you have an ID here. That means pick rule number 5, so on and so forth. Okay, so these grammars are called LL1. There's a whole branch of research that has classified grammars into all of these different categories. The first L means that we scan the input from left to right. The second L means that we do a left derivation. And then 1 means how many look-ahead symbols we need. Basically, how many tokens we know we need to have cached so we know which choice to make. Because we only need 1, because that's the number of tokens that we make a decision on, this is LL1. So these grammars are also called predictive grammars. And what's nice is that many programming languages are LL1. And we're going to see that this actually makes writing our own parser not too bad. Okay, just as a note, not all grammars can be written like this. All grammars, you can write them in a way that aren't left recursive, so that's nice. But not all grammars are LL1. For example, and sometimes you have a grammar like this. Imagine you have something that, a factor that could be an ID, or maybe you allow array indexing. So array indexing could be an ID followed by square brackets, or an ID followed by parentheses if you want to call a function. If you were to try to get the first sets here, well, for each of these rules, it's an ID. So this doesn't help us, because what this means is if we're looking to match an ID and we need to make a choice between 1, 2, and 3, we don't know which rule to pick. So this one is off. Lara?
Yeah, can I ask a question about the previous one?
Yes.
Yeah. So there, when you were doing the follow save for expression 2,
Yes.
so I guess the grammar always has to start with the start symbol with expression, right?
Yep, so this is a start symbol.
That's why we can have expression 2 and then, for example, of following.
Yeah, so technically there is a terminal here, none, because that means that the lexer is done parsing.
And then why, if it always has to start with the starting symbol, when we were talking about indirect left recursion, and we like translated it, we had like our expression base, and then we had an expression of, but we left it in case another production will reference this, but we need a reference.
Oh, yeah. In that case, we're not going to spend too much time talking about indirect left recursion just because it doesn't show up too often. That's just to kind of say that the recipe still works there. You just have to inline and then follow the recipe. And when you inline, you can't always delete the production option. Yeah.
But if none of the other rules reference it, then we would, right?
You could delete it. Yep.
Thank you.
Good question. Okay. So sometimes, so first off, not every grammar is LL1. And sometimes grammars that are LL1 might need to be rewritten. So like I said, in this case, these 3 options all correspond to the same non-terminal. But they all have the same first set. Whether you're trying to match, like a variable name or an array base or a function name, our first sets are not going to be disjoint. So that means in a top-down parser, you're not going to be able to tell which rule to pick. What you can do is you can refactor the grammar. So for example, you might have a factor, which is an ID, and then you might make a new non-terminal called optional args. And that optional args could have a open or array indexing with square braces or function call with parentheses. And then what you do is then you can actually get disjoint first sets, because now your factor only has one rule that matches an ID, and when you go into your optional args, you have open bracket and open parenthesis. You will have to do the follow set for the empty string there, But as you can see, you can refactor to get those disjoint first sets so that you don't have a backtracking grammar. Yep?
I'm confused on why we add the closing parenthesis or bracket to the end of the empty string follow set.
Let's see. Up here, right?
Yeah.
Okay. So I do think it makes sense to say that there's kind of this secret terminal up here, none, which is when you're done lexing. So with the follow set, you need to say, what can follow an expression 2? Okay? So then you go over here, you kind of do a search for expression 2, and you say, what can follow it? Well, there's an expression 2 here. Nothing really follows it there, so that's fine. Actually, and then you come up here and you say, an expression 2 is here. Well, what can follow that? Well, none can follow that. But actually, maybe it makes sense to that none isn't always necessary, right? So what you say is, a none can follow here, but also, this is at the end of an expression. So this is where the recursion starts. You now say, we're at the end of an expression, so what can follow an expression? And then you say, what can follow an expression? Well, that's where expression appears, and we have a closing parenthesis there.
So we have to recurse back along.
Yeah. Every time you're at the end, so there's an expression 2 here also. This is at the end. But because it's self-referential, we've kind of already closed that recursive loop. When you come up here, you say this expression 2 is at the end of an expression. Now you have to recurse and say an expression is here. And if we had expression appear someplace else, and it was at the end, then we'd have to continue recursing. Yep.
So when you say the grammar needs to be refactored, is that technically a case of eliminating either left recursion or left associativity? Or I'm a little bit confused on the terminology.
Right. So this is all just changing up the grammar to give it nicer properties that are easier to parse. So when I say refactor this one, your refactoring criteria is because your first sets are not disjoint between your rules. And what you're doing here is you're not removing left recursion. You're essentially refactoring it so that you get disjoint first sets. Yep. So it's a new thing. Yep. I don't think this shows up in your homework though, at least not kind of the natural ways. But it is. If we were to do arrays and functions, it would show up. Yep. Okay. Yep. Camden. Let's see what the follow set would be. So what the follow set would be is we'd have to see what can follow optional args. Well, what can follow optional args? According to this, assuming this is our full grammar, then it's just none, right? Because this would be our starting symbol. So yep, it would be none. Probably this is a snippet out of a bigger grammar, and then you'd have to kind of recurse back and see you'd have to say what can follow a factor at that point. Yep. Okay. Yep.
Is there a difference between writing none, like N-O-N-E, or just the empty string like that?
Yeah, because what empty string means is that it just matches the, anything matches empty string, and it doesn't pop anything off. None is the actual end of your string. That's what your lexer returns when it has nothing else to parse. So that means you're at the end. So you wouldn't want to say none here, because that means that's the end of your file. You're completely done. What this means is, it's optional. You can match an opening, you can match array indices, you can match function calls, or you don't match anything, and you just are finished parsing optional args, pop back up to the factor, and pop back up to wherever you need to go.
But when we're writing our follow sets, like in the homework, we should write because does it match? Or
You should write none if you're trying to match the end of the file. If that's the token that you're looking for, that you're done parsing, that there's nothing else after that, that's none. You should write empty string if that's what it is. If it's an optional, if it's something that's optional, then that's empty string. And that will appear in when you apply the rules to get rid of left recursion. That does appear quite often. Yep. Okay. So Ant actually has an animation. Do you want to show your animation?
Yeah.
Do you have it on yours, or do you want to use mine?
Do you have it downloaded?
No, but I can real quick. So give me 1 sec. Ant has a nice animation to show. Let's see. Download. And it is downloaded now. Okay. And do you want to present it, Ant?
Sure.
Yeah, I think you press space should go.
All right, pause. 1 second. Wait, how do I click this?
There it works.
Okay. Been a while since I've done this. Anyways, can everybody hear me? Alrighty. So, yeah, you just saw the first and follow sets, and well, let's take a better look at it. So, here's our grammar, and let's have our first sets to the side. So, if you're constructing first sets, how would you want to start this? Would you want to start from the top down or from the bottom up? Anyone? Yep. Exactly, and let's see that in action. So, going from the bottom rule, we just take the first non-terminal that we see and we just store it over there. So you have your asterisk, then your plus, and then your ID. And going up, your left parenthesis. So now we're at expert 2, and the process is the same. You have the empty string, but now at the up, it's not an well, it's a non-terminal, isn't it? Right? So we have to go back down to up, and so we walk back down, and we look back at our terminals. And going back up, there we see it again. And again with expert. And now we go down to unit, and we repeat the process. Are we done here? No. So, moving on, let's make a little more room. And now for our follow sets, just as you'd explained, you need we can put NAs for everything except for what? 3. And why is that? Because it's the empty string. Exactly. And let's just let it run. And now, how exactly do we want to proceed here? Go ahead.
We want to find all the places that expert 2 can go.
And we want to focus on expert 2. So we have to look back from the empty string, move up to expert 2, and let's focus on that. So we see expert 2, and there's nothing after an expert 2, so we can start off with a none.
And I actually think you get the none when expert 2 goes up. So.
Oh, well, that too.
Yes, so that's coming.
Yeah. And you bubble up, but you see that expert 2 is the end of an expert, but what can come after an expert? Yeah? Yeah, and so walking back, we see a right parenthesis after that, and we're done. And, well, there's only one thing left. And there you have it, the first plus set.
So, and you'll release that,
Yeah.
right? So, Ant will release that. It's been kind of fun putting those together, and so thank you, Ant. Yep, question? So the point of the follow set is you eventually want to get the first plus set. What the first plus set does is it means that if you have disjoint first plus sets for each of your options. So if I have this color coded, because expr goes to purple, expr2 goes to blue, unit goes to green, op goes to yellow. If these are disjoint in their colors for the non-terminal, then this means that you have a backtrack-free grammar. This means every time you have to make a choice on which rule to expand, you can make that choice because your lexer is telling you the next token that you need to match. So if you find yourself needing to make a choice on expr2, you can apply rule 2 or 3. You just look at the next token you need to match. If that token is a plus or a multiplication, then you pick rule 2 because you know that's the next terminals that you need to match. If you have none, that means you're done lexing, or if you have closing parenthesis, then you know that you need to take rule 3. So this is going to become a little bit more clear as we start talking about the next type of parsing algorithm we have. So like I said, you use your first plus sets when you're deciding which rule to pick. Specifically, you compare toMatch. Remember, you get toMatch from your lexer. toMatch tells you that token, the next token you need to match. And then when you need to pick a rule, you compare toMatch with the first plus set, and you find which one your token is in. And that gives you now this grammar that you don't actually have to make a choice here. You know what that choice is going to be. So let's move on and let's actually see a much simpler parser implementation. Again, this is what you're going to do for your next homework, but the first plus set is actually going to allow us to write quite a simple parser. And these are called recursive descent parsers. So I want us to think recursively, and I want us to think kind of how we describe things like this in English. How would we parse an expression? Like if this is our top symbol, how do we parse an expression? Yep.
We call a function to parse unit.
Yeah, exactly. If we want to parse an expression, we need to parse a unit followed by parsing an expression too. Well, maybe we can just write that in Python. If we want to parse an expression, parse a unit, parse expression 2. That's, this is going to be the beauty of recursion, is you just tell it what you want to do. How do we parse an expression 2? Well, we have to look into our first plus sets, because now we have a choice. We have a choice to make. When we're in parsing expression 2, we have to know the next token that we want to parse. We're going to get our token ID. So that's basically the next token that appears from our lexer. So we're going to get that token ID. So rule number 2, plus and multiplication. So if our token ID is in a plus or multiplication, then we're going to pick rule number 2. And if we pick rule number 2, then we need to parse an op, we need to parse a unit, and then we need to parse an expression 2, and then we return. The other option is if we're in to pick rule number 3, that means our token ID is in none or it's a right parenthesis. And if that's in our first plus set, then that's the empty string, and that just means that we get to return. We don't have to do anything. Everything matches the empty string. We just return. And if we don't see any of those, then we have a parser exception. That means we're not going to accept that input string. So we just can raise our parser exception. We probably want to report the line number. But now, when we're writing a compiler, sometimes the compiler will actually say, hey, I expected a semicolon. Hey, I expected a closing parenthesis. We can actually encode that. We can say, hey, I observed, this is what I'm trying to match. This is the token that I'm trying to match. But I expected either a plus, a multiplication, a right parenthesis, and I guess in this case, none would be included there as well, because those are the symbols where I could have made a choice. But you didn't give me any of those symbols, so I can't make a choice, and I have to stop my parsing. So this is getting even more informative error messages for us when we have to stop. Yep.
So fly recognizes none as the end of the file, but when you're actually writing your parser, would you use none instead of just an empty character?
You can kind of you can kind of do whatever you want as long as your lexer and parser agree on what that is. Yeah, and in ours, for the scanner we implemented for homework 1, I think we return none. So that's why I'm using none here, because when you write this, you're going to plug in your lexer that you wrote in homework 1, and then write this as your parser. Cool. Does that make sense? Okay. Let's look a bit more. If we want to parse a unit, well, how do we parse a unit? Well, we have options. If we pick rule number 4, we need to go to our first plus set. So if we are matching a left parenthesis, then what we do is we need to, what I call, eat the left parenthesis. I'm going to say we're going to eat that left parenthesis, and then we have to parse an expression, and then I'm going to say eat the right parenthesis. And what I mean by eat is make sure that the token that we are looking at is a left parenthesis. In this case, we know that it is because we just matched it up here, but we don't have that check here. So eat basically says, look at the token that you're parsing next, make sure that you match, and then get your next one. So eat is sort of moving along in the lexer. And then, how do you match an ID? Well, you just go to your first plus set. 5 is ID, so if your token that you're trying to match is an ID, then just eat an ID and then return. Otherwise, throw that exception. You were looking for a left parenthesis or an ID, and you didn't get it. And then, similarly, an op is basically the same. Check if you have a plus. If it is, eat it, return. If you have a multiplication, eat it, and return. Like I said, eating is going to your scanner, making sure that token is actually a plus, and then getting your next one that you need to match. And now what we've done is, because we have the first plus sets, that took some staring at our grammars and doing a bit of analysis. We removed left recursion, but we have implemented a parser in not that many lines of code by basically translating what we have here into English and doing a couple of conditional statements on the next symbol that we're looking to match. So I think that ends up being pretty powerful, and it is what you will be doing for your next homework. But thanks to this homework 2, you will have your grammar written in a non-left recursive way. You'll have your first plus sets, and then you can essentially just write them down like this, and you will have a parser, and you won't have to rely on ply anymore. So I don't know. I think that can be kind of fun. And you are going to bring in your own scanner as well. So that's how this is all going to come together. And I know it can feel a little bit long to sit through and talk about left recursion and first plus sets, but this is how it all kind of comes together nicely in code. And yep.
Will there be a model solution released for the scanner first?
Yeah, so that's why we can't accept late work, because I will release a model scanner and a model grammar and first plus sets. And then you can use your own, which can be quite nice, or you can start off the base. Yep. Okay, that said, it is 3:45. It is Friday, so go enjoy your weekend, and I'll see everybody back on Monday. Thank you.